Okay, now briefly. We had f of x, g of x formulas, we have f of g of x, we have g of f of x. We want to get the formulas for f of g of x and g of f of x. Now, you haven't done that, again, if you're just a student doing this video, do it before you see what has to be done. Make sure you're getting it right. Don't even look. Okay, hopefully you've done that. And of course, we have another problem here that you should do before we look at it. So maybe stop and do both of these as best you can and then move on. Okay, that's all covered last week. If you're a distant student, you need this stuff right now. Some of it you need last week, rate of change. This is going to be due on Thursday if you're in the distance class. If you're in a different class, not mine, not the distance class, not sure what your schedule is. Just try to get that to the instructor. Okay, so how do we do this? We write the formula for F. There's the formula for F. We plug in g of x, meaning x in the formula becomes g of x. Now, if you replace x in the formula with g of x, this is what you get. It should be clear. There will be parentheses around this, just to make sure you're squaring it, not thinking you square x. You're squaring g of x. Okay? You put the parentheses there to emphasize that. Then g of x squared, well, you take the formula for g of x, replace g of x by its formula, and there it is. Okay? Now to do g of f of x, you have g of x equals 2x plus 5. There's your formula for the first function, okay? Like when we did f of g of x, we started with the formula for f. We do g of f of x, we start with the formula for g. Could be done in a different order, but I'm not going to confuse things with changing the order. Okay, so formula for g of x is here. And what do? We've got to plug in f of x, because f of x is in the parentheses. So if we put f of x in the parentheses where x is, then we get g of f of x. And if we put f of x in there for this x, we get f of x. So we plug in f of x, and we get this. A simple three-step problem. You ought to write out those rules in that order. Okay. Then if you see it in a different order, it's pretty easy to modify the rules. We're going to end up with the same thing either way. Write down the algorithm. This step, this step, this step. Okay. Well, there it is. Now we have g of f of x then equals what? Well, we replace f of x by its formula. The formula is x squared for its equation. Okay. So f of x gets replaced by x squared. And there we have it. Okay. Mentioned a little bit about the domain. Any x works here, any x works here. There are cases where f of x or g of x could have a restricted domain. For example, if f of x was the square root of x plus 3, then you couldn't feed any number less than 3 into the f of x function. And we can't talk about that because of all the delays with snow schedule and stuff. The distance class is way ahead of at least my in-class section. And I think it's probably well ahead of the other one just because they didn't have to miss any time. We missed quite a bit of time. Okay. Okay, so anyway. Now we find the average rate of change of f of x equals x squared in the interval -1, 3. Okay, hopefully you've done this. Hopefully you've got it. But we'll see. I've got this question. Okay, f of x equals x squared, talking about this problem now. As x changes from -1 to 3, f of x changes from what to what? So be sure you work that out before I show you. Okay, now this idea of taking the formula and replacing x with something is giving some people a huge amount of problems. Okay, it's giving everybody some problems. So I assume that it's doing that for people who aren't here today, and I assume it's doing that for some distance students. Okay. You notice here, I replaced x by g of x. meaning this x becomes g of x, this x becomes g of x, right? Here, we replace x by f of x. I said plug in f of x. That means replace x with f of x. Okay, replace x here with f of x. So this x becomes f of x, this x becomes f of x. Every x in the whole formula will become f of x. If you write this, okay? Now, if you write f of x equals x squared, f of -1, well, why would you write f of negative? How do you write f of -1? You replace x with -1. Well, then it should be automatic. You shouldn't even have to think about it, but of course, most classes you change it, you know, do that without thinking about it. You replace x with -1. So that if you square -1, you get 1. Then we've got, again, f of x equals x squared. Well, now we're going to do this for x equals 3 because we're finding the change from -1 to 3 because that's the interval. We take this number, and we take this number, and we plug it in for x. So we have f of 3 equals 3 squared. So f of 3 equals 9. Okay, so f of x changes from 1 to 9. Now, okay, average rate of change is average rate is change in f of x divided by change in x. Okay. Now, we know that f of x changes from 1 to 9. Okay. How much changes that? If something changes from 1 to 9, by how much did it change? Can you hold up fingers and tell me? If you got $1 and then you got $9, how much did your money change by? Hey. Okay, how do you get that? You do 9 minus 1. Okay. So this equals 9 minus 1 over, I'm going to use delta for change in x, over delta x. Okay, so we've almost got it. What's the change in x? Well, x changes from what to what? Now, I don't want you to write anything more down. I want you to put two numbers that answer this question. What are the two numbers? Put down two numbers in your paper that you have to use to figure out how much X changes. What two numbers are you going to use? Well, X changes. X changes from -1 to 3. Okay. So how much change is that? Well, we need to move on to some other things. So I'm going to have to tell you. Give you just about 30 seconds. Can you write down how you would calculate the change? Or can you tell me, can you show me with your fingers what the change would be? Well, you're going from -1 to 3. You can visualize that. Here's the number line. Here's -1. Here's 3. How far do you have to go to get from here to here? Hold the hand out straight. Put your thumb out or in. You want from -1 to 3, you go 0, 1, 2, 3. That's 1, 2, 3, 4 units. Okay. You're not going to count -1. If you count -1, you might think it's 5, right? Somebody had 5, okay? Which is close, but you're just counting how far you have to go, and you haven't gone anywhere when you're here. You don't go anywhere until you get to 0. And there's 1, 2, 3, 4 units. Calculate it by subtracting the first number from the second. So we can do arithmetic, we do it on a calculator. But we want to visualize it on the number line and reconcile it so we understand it. Because unfortunately, people don't seem to understand that there's a number line sometimes. Again, I talk a lot about how poorly our curriculum prepares people for thinking about this stuff. So you want to try to go back and think about these things. Okay. So now delta X is 3 minus -1, which is 4. Average rate is changing Y divided by changing X, which is then 9 minus 1 over 3 minus -1, which is 8 over 4, which is 2. Now, that goes on a graph. If Y equals f of X, X goes on this axis, then when we have -1 here, and we have 3 here, at -1, the Y value is 1. So let's see, we're going to have to have 1, we're going to have to have 9. So I'm going to put 8 here. And 4 would go here. 2 would go here, 1 would go here. So this dotted line through here is y equals 1. We also have 3, and we have 6, and we have 7 and 5. Okay, we have all those numbers in the y-axis, and then we have 9 up here. So if x is -1, y equals f of x is 1. We calculate it. Okay. F of -1 is 1. If x is 3, y, which is equal to f of x, is f of 3, which is 9. So by this point and this point. Now, as we did in my class, we sketched what we call a fundamental triangle. Actually, I think we did that in this class. We sketched this triangle, okay? A line from here to here, and we'll make it an arrow. And we have an arrow that goes from the leftmost point to the right. And we have a run. And the run is your change in x. X changes from here to here. Well, the run goes from here to here. There it is. And the rise is 9 minus 1, which is 8. The slope is the rise divided by the run, and that is the same as the rate of change. It's 8 divided by 4, just like the average rate is 8 divided by 4. Now, I'm not going to complete labeling this, but review how we labeled this triangle. If we labeled it in this class, I'm not sure we did, but go back to what we did last time, relating this to the triangle, because I'm pretty sure we did that. Okay. If not, well, just take what we have here. Rate of change, average rate of change is a change in average rate of change of this with respect to that is change in this divided by change in that. This average rate of change is change in the value of f divided by the change in the value of x. We can represent that on the graph by this triangle, change in x here, change in y, which is the change in f here. In the slope, we divide the rise by the run, you get the same thing you get here. Okay, now we want to talk a little bit about transformations. If you're in my class, you've seen it in a sense, but not in the sense we're going to look at it. Okay, so we're going to do first summary of transformations. Transformations of the graph. Now, I want to start out with the idea of transformations of a rectangle. Here's your original rectangle. Here's your original rectangle. Now, we're gonna call this dimension. I was gonna call it H for height. Um. And I'm gonna call it L for length. And W for width. Don't want to use 8 because we use that for something else. Okay. Now, rectangle's still going to have width W. Yeah, this is still label it properly, but it's there. You know, regard the horizontal as width. Okay. Horizontal side is width. And they're called the height A times L. Okay. Now, how much higher is the second rectangle than the first? This is how high the first one is. The second one is about, I'd say 1.6 times as high. It's not twice as high. If it's twice as high, it would have to be this much. It has to be all the way up to here. But it's clearly more than 1 times as high. So I'm estimating that it's about 1.6 times as high. Okay. So there's our vertically stretched rectangle. Picture. Sorry for doing all this writing. Well, lots of board, but the stretch rectangle in the picture is 1.6 times as high as the original. So for the picture, A equals 1.6. Okay. Now I'm going to sketch a parabola, a symmetric parabola in each rectangle. So what I'm going to do is I'll do them side by side. I should have thought before I started the picture. Do what I wanted to do first, but that's what I'm going to do here. Okay, so the first picture is here. And a parabola that goes through this point and this point in the middle of the base. It's going to look something like this. It's not a great parabola. Now in my class, we've learned how to construct these parabolas without using any numbers. But of course, if you've been through the assignment on the toolkit functions, you know how to use numbers to create this. I chose not to use numbers because people at this point can't be relied upon to understand how to do the arithmetic to get the numbers. And we don't want to just do it by calculator with the idea that we're actually learning anything significant. Well, we are, but we're not really learning what's going on if we just get the numbers from the calculator. So in my class, we're doing it a little differently than others. But whichever way you do it, you know the parabola could look like this. I haven't put a scale on it, I know what a parabola looks like. And you know what I mean by going through this point, and this point. So you just draw a parabola that looks that way. Okay, well, if we do it here. this rectangle has been vertically stretched. So if we do a parabola using the same idea, goes through the upper corners in the middle of the base, it's a vertically stretched parabola. Now, if this parabola is y equals x squared, then this parabola this parabola is ax squared, and if this is 1.6 times the sine of this y equals 1.6 x squared. There's a good reason for that. Your y coordinates go this way, and if everything is multiplied by 1.6 in this direction, then you're going to have to multiply 1.6 times x squared. Right? Now that also works for any function. So if we have y equals 2 to the x sketched in a rectangle, and over here we would have y equals a times 2 to the x is 1.6 times 2 to the x. Now, you might not have seen 2 to the x function. I think it needs to be introduced right at the beginning of the course along with the others, because it's easy to construct and it's easy to calculate if you don't try to calculate it for fractional values of x. Okay. Or we could do y is 1 over x. It might have a graph that looks like this, if your origin is here. Okay. We could do the same construction over here. We have a graph that looks like this. Just giving you a general picture. Well, what you conclude is if you have y equals 1.6 over x, then you can just think of, well, let's just draw a graph of y equals 1 over x and some kind of a rectangle. Okay. And then stretch it out by a factor of 1.6, and there we have it. Okay. There's much more that can be said, but that's the picture. What you do. Now that's in some ways a little less obvious, but in some ways more obvious than some of the alternatives. Okay. So now let's just say we have a graph of y equals x squared. Okay. Now we can put a box around that. We don't have to, but it kind of helps us visualize what's going on. So I'm going to put a box around this using the upper corner and the vertex. Okay. Now I can move this box. Okay. If I move this box to here, without changing its length and its width. Then I can sketch a rectangle. And I can sketch the graph inside. Now that works if we have a graph of x as a function of the reciprocal function of the cubic function or whatever in our box. The box moves. I'm going to just take the center of the lower edge of the box and see where it goes. It goes over this far and it goes up this far. And well, coordinates of this vertex here are 0, 0. That's the coordinates for the tooltip function. And the coordinates of this point, well, I'm going to call the coordinates H for horizontal. Okay, doesn't stand for much better thing, but it's the vertical. Okay, so we move H units horizontally and K units vertically. So everything moves H units horizontally and K units vertically. And the new function is y equals a quantity x minus h squared plus k. Now, in my class, we've done instructions to give us the change solution. Most important of the toolkit graphs. And we've convinced ourselves, if we've done everything that we're supposed to have done, we've convinced ourselves that this really works, that if we have this function and we pick an x value and look up here and estimate what the y value is, it'll match this function pretty well. Our estimate will match the reality pretty well, so we understand what this function is representing and we understand everything within the plane. Now, depending on how well you understand what the geometry and the coordinate plane, that might or might not make sense, but it is what it is. If you draw this, if you draw this accurately and then accurately draw this, and then pick an x value that is your point on this graph, and estimate where the y value is, and then plug that x value in here and evaluate this, you're going to get the y value. It's something very close to what you would estimate would make perfect sense in terms of your picture. Gives us the big idea. Now, if you're not in my section, you'll not understand that as well as people from my section probably do. That's what's going on. So that's all I'm going to mention about what goes on in my section. The whole point, the whole picture though is if you move any function take the graph here and draw any box we want to around your function. Okay. So let's just say your function looks like this. Okay. Inside the box, you see what we have here. Now, if we move that box down here over H units and up K units, of course, K would be negative. Then we take a picture of whatever's in the box. And it should look exactly the same. I didn't make my box wide enough that you get the idea. Okay. And then we can draw whatever's outside the box too. If we know something. Okay. And so if it goes on outside of the box here, okay, maybe it comes out of the box like this. If this is y equals f of x, now if we move H units horizontally and K units vertically, this graph is y equals f of x minus h plus k. That's a little confusing. You have a minus h and a plus k. I could explain the reason for that. I'll just say it. It might not. It needs to be said more slowly and more detailed. We only got a few minutes. In order to give you the same value of f of x, x would have to be h units bigger here than it is here, which is why subtracting h moves the graph to the right. Now, plus k, you know, this is the y value of this function. We add k. Now, k is a negative number in this case, so adding k would give us a minus number. It's just, that's how far y values change. That's the amount by which y values change from here to here. The corresponding things. And there it is. I didn't state that very well. That's in a nutshell, but of course, got to be in a nutshell because we're almost out of time. All right. So the basic rule. Now there's more. There's horizontal compression that I'm not going to take time to talk about. Let's understand vertical stretch first. Okay, the rule is if a vertically stretched graph of f of x by factor a then we shift h units in the horizontal direction. K units in the vertical direction. I've got to abbreviate the space of time.
So, have a good day. Thank you.
Our new function is y equals a f of x minus h plus k. Now, in my section 3 calculus, done quite a bit with this. We're gonna do quite a bit more today. But there it is. That's the rule for transformations. Now I'm covering that rather quickly today because people in the distance section especially gonna need that this week. Okay? With an assignment that's due Thursday. So hopefully this will be helpful. We'll talk a little bit more about it in the next class, which will still give people in the distance section a day before their assignment in that class is due. But this also works well for my class. Especially in my class, you probably recognize this a lot better. Since we've taken so much time to construct these graphs and move them around, okay? So that serves as an introduction and a reinforcement, and I hope it works for the other section and maybe something. Okay, very good. Okay. Although if you did walk in front of, probably make everything look better. And you're not in this class, so wouldn't compromise your identity.